Let's start visible.
Okay, guys, so let's get started. Today I'm intending to just familiarize you with interest line for trusses. We have done so far the interest line for determinate structures, which involve mainly beams. And in case of beams, we use Muller and Brusler principle to draw the influence line for beams. Okay, depending on our variable of interest. In case of trusses, you can use Muller and Brusler principle, but the problem is that it becomes mathematically too much involved. So therefore, it's not normally used. The principle is not normally used for trusses. We can use, like from the first principle, we normally find out the influence lines for trusses. We can use the Muller and Brusler principle for the reactions. Reactions are the same. In the case of Muller and Brusler principle for beams, we had the restraint removed, and then we moved the structure by a unit displacement, and and the deformed profile gave us the influence line diagram. In case of trusses, truss reactions, we follow the same principle. Okay, so if you are intending to find out any reaction, you remove the ability to resist that reaction. So you omit that reaction and move it by a unit displacement, and you will get, the same triangular variation. Okay, so reaction is okay, but first of all, let me introduce you, like in case of trusses, why do we need influence lines? Influence line, mainly, I told you that the its main application is in bridges or in those structures which have got moving loads. Okay, so it can be obviously bridge have got moving load, but beside that we have in industries we have got big girders which are moving big piece of equipment from one place to another all the time. You might have seen, you might have visited the car mechanic shops. Yeah, over there they are lifting the engine, moving it through pulleys from one place to another. So obviously there is a big beam which is doing that for you. So that is also a moving load all the time. It's not a static load. So that is also one application of these beams of influence lines. Now, where can we find trusses? Trusses can also be found in bridges, okay, and it can be found similarly, in industrial buildings. So, in case of bridges, what happens is that you can have okay, so we can have two types of scenario. Imagine we have got a bridge. The bridge supports a road, isn't it? And that road is then supported by a structure. It can be a big girder, a beam, okay, or it can be a truss structure. And that load is then transferred to the ground. As I told you in structure analysis, you are transferring the applied load to the ground, and you have to provide an intermediate structure to do that for you. And in the case of, so you can have two types of scenario. Either the bridge is hanging down, something like this, it's sticking down, and you have the road on the top. So we have a road over here. Okay, so we can have a road, and these can be two banks. Okay, we can have big piers on the two banks. In the middle, we can have a river or a valley or whatever. Okay, so in this case, you have got the moving load, which is going like this, and obviously as this load moves through the bridge, you can have loads developing in all these members, isn't it? And with the movement of the loads are going to be different. Do you understand my point? The thing is, normally if we have got the road, so this is connected at the joints. Normally the roads are connected. This girder, it can be a girder or a girder, and that is connected at these joints. Okay, so whatever load you have, that goes into these joints as a concentrated load. Are you getting what I'm saying? A truss cannot take a UDL. A truss will always take a point load, isn't it? So I have placed, I've got this truss structure. On the top of it, I have put a girder. It can be a concrete beam or it can be a steel beam. Okay, and on that I have got a road surface. Do you understand? So there is a road surface, and underneath it there is a beam, okay, of any material, and that beam is connected only at the joint. If I join this beam with these members also, then UDL will start getting transferred to my truss, which I don't want. Truss can't take UDL. It can only take it can take loads at the joints, and as a result, the load is then transferred through axial load. Okay, sir, please. Thank you. Please. Okay, so and then after that we have so that's one scenario. The other one is that our the road is over here. Okay, now this is a very common structure which you might have seen in our country also, if you have seen. Okay, this sort of structure is when you are going to Lahore. I have seen many bridges like this on motorway. Okay, so this is a very common structure where you have got road over here. It can be a rail bridge or it can be for vehicle, whatever. But you have a road over here, and the load is getting transferred like this. Okay, so when your load goes from this joint to this joint, and there can be many joints in the middle. Okay, I've just drawn it very simple, but you can have many joints like this one in the middle. So when the load is over here, you will have one set of loads in the internal in the members, isn't it? And as the load moves to this point, then you will have a different set. And similarly, when it comes over here, you can have a different set. So how to find out? So if you are asked to draw influence line for a particular member, then unfortunately you have to go and do that via first principle. What do I mean by first principle? You first of all take a unit load over here. So obviously no load is going there. Okay, no load is running into the truss, isn't it? When the load is over here, all the load is being transferred into the pier. Then you put it over here. Okay, so I might ask you to draw influence line for this member. Okay, for this member. So you will do either method of section, or the method of section is normally easy in this case, and you will find out your load over here. Okay, then you will come here, bring the load over here, and again find your load over here, load in this member, and then you will bring the load over here, and again find your load in this member. Do you understand my point?
Yes, sir. Yes.
And similarly, if I ask you, similarly, I can ask you to draw influence line for this one, for this member, which is the top chord member. So you can have the same thing. Now, how do you do the sense check on it? Do you understand any question about influence line for trusses? It's the same thing what we did previously. Okay, simple structure analysis of truss. But now you have to do it with a moving load. And how do you do that? I've given you a truss, first of all, and based on the joints. Okay, so you place the load at one joint. Okay, then find out the force in this. Then you place the load over here, find out the force in this. Place the load over here, find out the force, and you draw a table. So in the table you will have x, which is meter from the support. So x is in this direction. Yes, and then you have these members. So for example, I've got A, B, C, D, E, F, G, A. Okay, and I'm asking you to find out the loads in three members. Say one is A, so this will be kilonewton. One is in BC, again kilonewton, and one is in, imagine one of the brace, which is BG, and that is also kilonewton. Okay, so you will have so depending, I mean, like how many joints you have. So the first, these are 4 joints, so I would have the first one at x is equal to 0. Then I would have at x is equal to 4, then 8, then 12, and sorry, 4, 8, 12, 16, and yeah, that's it. So, and then you can find out the forces over here. When your load is over here, so what is the force over here, force over there, and force in this one. Now, so that's how you draw your influence line, and then after that, let me rub this off. You have to draw a sketch. So again, this is a determinate structure, so the influence line is going to be linear. So okay, so I have x in meters. So this will be 0, this will be 4, this will be 8, 12, and 16. And I would have the value of AH. Okay, so you will see that. Okay, now let us do some sense check on this one. Okay, sense check means that what would be the direction of our influence line? That's all we can tell. Now, if the load is applied over here, obviously this bottom chord, this will be in tension, and the top chord is going to be in compression. So if my tension is positive, then that means that my influence line should be for the any chord member, any bottom chord member, it should be over here, and for the any top chord member, it should be downward. Okay, and in the case of braces, brace is like a shear. So you will see that as the load, so it will be something. So the brace, for the brace, normally your influence line diagram will become something like this. Okay, that is a common influence line diagram. And in the case of this one, either it will be over here or over there, but mainly the tension one can be something, imagine something like this. This can be tension, and the compression one can be something like this, depending like where this is. But that's how, so this is going to be the compression one, this is going to be the tension, and for the brace you will see that there will be a drop down like here. That's how you draw. Okay, so would you be able to add this question also to your assignment? This is the third question. Okay, in that assignment. No. You have to give me what you need. This is, I mean, like these are important questions from exam point of view. So now this one please add, because I want to then check it whether you have got it. Because this is very straightforward. The only thing is it is a bit laborious, a bit time consuming, but in general it is. Okay, so yesterday I gave you 2 questions and add this question also. Okay, you have to draw influence line for AX, BC and BG. Have you written it down? These 3 I need please on Monday, okay? And please don't give me late assignments. Okay, because don't come up with these excuses. I'm giving you enough relaxation. So I mean, like, if you want to do it in time, please. Okay. Okay, I agree. If we agree Tuesday, we'll give me on Tuesday, okay? On Tuesday, the same after the class. Okay, so yes, I give you that. But please give me that. Today, 2-3 guys came. Some was saying that they have got short memory, some have got long memory, some memory is not. I mean, like different type of excuse. Okay, so what I'm saying is that this is your influence line diagram for the trusses. Okay? Any question? Okay, just one simple thing and that's it. Okay? A simple thing. I'll start that in the next class, but I want to tell you just 2 applications of influence line. Okay? 2 applications. Okay, applications of influence line. Okay, now as I told you, essentially we have 3 applications of influence line. Okay, the first one is that in like whatever we have done so far, that is that if you have any member which is subject to a moving load, you are able to find out the moments at your point of interest. Okay, so and from there you can judge whether you have maximum moment, whereabouts can you have maximum moment. Okay, so that is the first application. But the influence line diagrams can also be used in case of statics, and let us see how can we use it. Okay, for example, imagine I have a beam. Okay, we have got a beam which looks something like this. Now, the second application is that influence line can help you overcome the equation of equilibrium. Without writing the equation of equilibrium, you can find out your variable of interest. And what do we mean by that? Now, if we are asked to find out reaction, okay, reaction at A, RA. So help me out quickly. How would we do that? Reaction at A. This is through normal mechanics, normal statics. How would we find out the reaction at A? Yeah, so RA. Okay, so reaction at RA. Okay. So we have RA times, help me out, 20, 80 minus 1.3 into 20 into 20, 20, 20, 60 and 70 minus 25. Please get your calculators ready. 25 into 40 minus 42 into 20. Help me. What is RA? Come on. This is using statics. Equilibrium. Okay. What is RA?
45.75.
45. Is it okay?
Yes.
Yeah?
Yes, sir. Yes.
Okay. This is our 45.75. Now let us use influence line to find out the same reaction. Okay? So influence line for the reaction is, what is the influence line for reaction? Okay, what is RB? What is RB? I mean, just subtract this.
47.25.
Huh?
47.25.
40?
7.25.
Is it okay? 47.25? Okay, 47.25. Yes, 47.25. That's okay. Now, let us use influence line diagram. In case of influence line, so this is RE, okay, not RB, RE. So for influence line diagram, for RE, what is that? Remove the ability to resist, the reaction, move it up and comes over here. You get 1 and this is 1, okay? And let us find out, this is quickly. This is 20 feet, 20 feet, 20 feet, 20 feet, okay? And what would be this one? What is the magnitude? So this is 1. What is this one?
26.
1 by 80 and y by 20. So give me this, hurry up. This one, and this one.
0.25.
Huh?
0.25 and 0.75.
Yeah. 0.25, 0.5 and 0.75. That is what we have. Is it okay? Now, what we do is we find out because we have drawn it for unit load. what we can do is RE is equal to 42 into 0.75 plus 25 into 0.5 plus 13 into half 0.25 into 20. What is this? Can you do that? 42 into 0.75.
1.3 uniform.
This is 1.3. Yes, this is 1.3 kip per foot. 1.3 into
For 7.25.
huh?
7.25.
So, what have we done? The influence line diagram actually gives us, as I told you, this is for a unit magnitude. Okay? And if you, in the case of concentrated load, you multiply the magnitude of that concentrated load at a particular location, okay, which is this one, you multiply that with this magnitude. The other load you multiply with that magnitude, okay, and then the UDL you multiply with the area. Okay, so why? Because it's a uniformly distributed load. That load you multiply with the area, with the whole area, because obviously it's per unit length. Okay, so you have to multiply it with the whole area, and you add everything up, you get the same reaction. In other words, if this is, I mean, what have we assumed? We have divided this beam into a beam which has got into three beams. Every beam has got, okay, so for example, so for every load we have multiplied the corresponding magnitude of the influence line. Okay, so if this one load is 42, so 42 times 0.75, what is that?
31.5.
That is if your unit load, in other words, if I've got this load as a unit load, then at this particular location, so what would be my reaction? Okay, that's what this influence line is telling me, isn't it? If I've got a unit load at this location, what will be my reaction at E? Okay, similarly, if I have got load in this location, the unit load, so it's the same unit load which is running, but the moment it comes over here, what will be my reaction at E? So that's why, so the reaction at E was 0.5, but in the reality I've got 25 kip load, so I can multiply that with the 0.5, okay, and I get the actual reaction when you have 25 kip applied.
Yes.
And then I have got now continuous, a uniform load applied. Okay, so this is per foot which is applied. So therefore, I have multiplied this area with it because it is per unit length. Okay, so I have multiplied this whole area. So in other words, the load which is over here, that is being multiplied with this one. The load which is at 1 feet apart from this one, that is multiplied with the corresponding length over here, and so on and so forth. That's why I have multiplied the whole area with it. Do you understand my point?
Yes, sir.
And then I have added all of them. Why? So I have three REs. One when the load is over here, another one when the load is over there, and the final one when I have got the UDL. I have added all of them and I get the same reaction. I can do the same thing for the other one also.
Yes, sir.
Thank you,
But
sir.
in the other one, please notice that in that case, I have to multiply the area of a trapezoid. Because I would get a trapezoid, won't I? If I move it in this direction, if I move, if this is like this, yeah? Okay, so my UDL 25 and this one. Okay, so I need this area. So for this area, I have to multiply the trapezoid.
Yes.
And then the same 25 with this one and 42 with this one, I add up. So I mean that makes it quicker, isn't it?
Yes, sir.
But that is the main, that's why someone asked me, why are we doing it for unit load? Isn't it?
Yes.
During the previous classes, someone asked me. So that's why, so that is one of the application of the influence line diagram. Okay? So in the next class, we are going to do the third application, which is how to find out the maximum. And similarly, we can find the moments also. We can multiply the same load with the moments, and at that particular point, you can find moments. For example, if I want to find out a moment at this point, so if I have the influence line diagram, I will multiply again the same thing. Everything is linear, and I will get my moments, shear, everything.
Thank you, sir.
Do you understand my point?
Thank you.
Thank you very much.